Imagine standing beneath the quiet night sky and wondering whether time itself is behaving the way it seems. What if the flow you feel inside your mind is only one version among many flows that exist in the universe? What if the passage of a second is not a universal truth but a local illusion sculpted by something deeper? And what if the pull you call gravity is not a pull at all, but the echo of time stretching and slowing around you? If time can shift and bend the way light bends through water, then what exactly are you standing on right now? A solid world governed by mass, or a shimmering fabric of space-time guiding your every step? These questions linger like whispers. They invite you to look again at the familiar and see something very different hidden beneath it. The universe that Isaac Newton inherited was elegant in its simplicity. The world appeared like a grand machine that followed rules as clear as the motion of a falling apple. When Newton formulated his law of universal gravitation, he offered a description powerful enough to predict how planets move and how tides rise and fall. In an age when scientific instruments were still crude compared to what came later, his equations worked with astonishing precision. They explained the sweep of the moon around Earth and the dance of Jupiter and its moons. Engineers and astronomers trusted these ideas so deeply that they built their world upon them. Yet behind the success of Newton's work, a quiet puzzle remained unresolved. He had written a rule describing how masses attract one another, but he never explained how this attraction travels through space. He himself admitted he did not know the mechanism. He only knew that the mathematics seemed to match the behavior of the heavens. Imagine two massive worlds separated by vast emptiness. In Newton's picture, each world instantly feels the presence of the other. No messenger travels between them. No signal carries information. The influence simply exists. This was called action at a distance, and although it worked perfectly in calculations, it troubled scientists for generations. How could something in one location change the motion in another place without any delay? The idea raised another problem. If gravity acted instantly, then it would violate the deepest lessons learned from the study of light. Even before Einstein, experiments had shown that light has a finite speed. If light needs time to cross space, how could gravity act without any time at all? Newton's theory did not answer this question. Instead, it quietly sidestepped it. Astronomers continued to test Newton's equations with ever-growing precision. Most motions matched the predictions beautifully, especially in the outer regions of the solar system. Far from the warmth of the lowercase sun, planets followed the elegant ellipses his mathematics expected. But closer to the center of the solar system, one small world refused to obey perfectly. Mercury possessed a slight irregularity in its orbit. Over a century of measurements showed its closest point to the lowercase sun drifting by a tiny but stubborn angle. The amount of this drift was about 43 arc-seconds per century. This value is so small that a human eye could not notice it, yet it mattered. Newton's theory could explain most of the drift by accounting for the gravitational pull of the other planets. But the remaining fraction would not disappear, no matter which corrections were attempted. Scientists proposed the existence of an unseen planet named Vulcan, but searchers found nothing. The leftover anomaly remained. By the late 19th century, this inconsistency had become a silent crack in the foundation of classical physics. The force rule that had guided 2 centuries of science seemed close to perfect, but not quite. The irregularity in Mercury's orbit was more than a loose thread. It was a sign that something deeper was hiding beneath Newton's description. The universe was hinting that gravitation could not be fully explained as a simple pull between masses. Something was missing from the picture, something subtle and profound. As researchers approached the 20th century, they also faced a broader shift in understanding. Electricity and magnetism had merged into a single unified theory known as electromagnetism. This new theory made it clear that influences do not travel instantaneously across space. Signals move at the speed of light, no faster. If gravity was truly instantaneous, it would break the rules that were already well established in physics. But if gravity was not instantaneous, then Newton's description could not be complete. The world seemed to be standing at a boundary between the old and the new. Imagine the sky again. Imagine the planets looping around the lowercase sun, each one guided by a law that works almost perfectly, but leaves a tiny residue unexplained. Imagine that hidden in that residue is a clue that leads not just to a new law, but to an entirely new understanding of space and time. Gravity was about to be reimagined. Newton had discovered the pattern. Einstein would reveal the reason behind the pattern. The moment Newton's ideas began to show their limitations, physicists were forced to look more closely at the nature of space itself. They had long imagined it as a silent stage, an empty container where events unfolded without influencing one another. Space was absolute. Time was absolute. This background never bent, never twisted, and never responded to matter or motion. It simply existed as a perfectly rigid framework. Yet this view did not match the deeper questions that were rising. If influences could not act instantly, then perhaps space and time were not the passive entities everyone assumed. Something about their structure might be hiding a richer story. By the time the 19th century gave way to the 20th, experiments involving electricity, magnetism, and the speed of light challenged the classical picture. The speed of light behaved strangely. No matter how observers moved relative to one another, the measured speed remained the same. This was not what classical physics expected. According to the older viewpoint, speeds ought to add or subtract depending on motion. Instead, light acted as though it followed a rule that refused to change, a rule embedded directly into the structure of reality. The implication was unsettling. If the speed of light did not depend on motion, then something else must adjust instead. That something was time itself. Einstein, still a young man working away from the traditional academic centers, took these facts seriously. While others wrestled with the contradictions, he asked a different kind of question. What if time is not fixed? What if time can stretch, slow down, or change depending on the observer's motion? What if the universe adjusts time itself to preserve the speed of light? These questions led him to a single conclusion. The laws of nature remain consistent only if time and space are intertwined into a unified fabric. Once this idea settled into place, everything began to shift. Time was no longer a universal drumbeat. Distance was no longer the same for all observers. The universe had a deeper architecture waiting to be revealed. This new understanding did not arrive all at once. Experimentalists were uncovering evidence piece by piece. High-speed particles in laboratory beams were living longer than expected. Clocks carried aboard fast-moving machines were ticking at different rates. Yet the idea was still forming, waiting for someone to articulate it cleanly. When Einstein published his work in 1905, the scientific world felt as though someone had opened a hidden door. Behind it lay a strange but coherent realm, where time slows down when objects move quickly and lengths shrink along the direction of motion. These results were not speculative. They were later tested with extraordinary precision and confirmed again and again. In the years that followed, the mathematician Hermann Minkowski recognized that Einstein's insights pointed to a four-dimensional reality. He showed that space and time cannot be separated. They form a single arena known as spacetime. Movement through this arena determines how time flows for each traveler. Faster motion through space means slower motion through time. The world was beginning to see that time does not simply pass. Time behaves. It shifts. It bends. It adapts to the circumstances of motion. This revelation forced a deeper question. If gravity was truly a force acting instantaneously across space, then how could it exist in a universe where signals and influences obey the speed of light? The picture drawn by Newton no longer aligned with the emerging understanding of space-time. Something had to give. Gravity could not remain a mysterious pull with no mechanism. It needed to be reinterpreted in a way that respected the rules of light and the fluid nature of time. The unresolved mystery of Mercury's drifting orbit now seemed more important than ever. It was a clue pointing toward a fundamental flaw in the classical worldview. The drift was small, but it was real. It hinted that the structure of space and time might not be perfectly rigid. Perhaps something deeper was guiding the planets, something that Newton's equations could approximate but not fully capture. Einstein realized that if gravity truly influences the paths of planets and light, then it must somehow be connected to the geometry of space-time itself. Space and time were not passive. They were active participants in the story. They could curve, stretch, and respond to matter. And if they could respond, then what people had always called a gravitational pull might actually be the natural motion of objects following the shape of space-time. The stage was set. Newton had mapped the motions. Einstein was preparing to uncover the reason behind those motions. What began as a small anomaly in a tiny planet's orbit was slowly revealing itself as the gateway to a new understanding of the universe. The next steps would be bold, imaginative, and astonishingly accurate. Einstein knew that answering the mystery of gravity required a change in perspective so deep that it would reshape the foundations of physics itself. He began by returning to the everyday experience of falling. When you drop an object, it accelerates toward the ground. But something about that simple motion contains a hidden truth. If you were inside a sealed elevator falling freely, you would float as though gravity had vanished. A dropped key would not fall to the floor. It would drift beside you. There would be no tug downward, no sense of weight, no evidence that you were in a gravitational field at all. This strange condition revealed something profound. The experience of free fall and the experience of being weightless in deep space are identical. Gravity, in that moment, seems to disappear. Einstein recognized this as a clue that gravity might not be a conventional force. It behaves differently from every other interaction known to physics. When you stand still on the ground, you feel the floor pushing up on you, preventing you from falling. The feeling of weight is not gravity pulling you downward. It is the ground pushing you upward. In free fall, that push vanishes, and so does the sensation of gravity. This observation led Einstein to his equivalence principle, which states that locally, the effects of gravity and acceleration are indistinguishable. It is one of the most beautiful and powerful ideas ever introduced into science. If gravity and acceleration are equivalent, then a beam of light inside an accelerating elevator must bend. Imagine shining a beam across the cabin while the elevator accelerates upward. Because the floor rises while the light travels, the beam appears to curve downward. This is simple kinematics, but now consider the equivalence principle. If acceleration and gravity are locally the same, then a beam of light must also bend in a gravitational field. Light, which has no mass and is unaffected by traditional forces, still follows the rules of the geometry it travels through. This bending of light near massive bodies was one of Einstein's earliest predictions, and it would later become one of the great experimental confirmations of his theory. The equivalence principle also reveals that gravity influences the flow of time. A clock placed deeper in a gravitational field runs more slowly than a clock placed higher up. This effect is extremely small near Earth, but it is measurable with modern atomic clocks. In the early 20th century, it was only a bold prediction. Yet the logic behind it was unavoidable. If acceleration affects time, and gravity is equivalent to acceleration, then gravity must affect time as well. Time itself, Einstein realized, could speed up or slow down, depending on the gravitational environment. This idea marked a turning point. Gravity was no longer simply a force acting on mass. It had become something more subtle, something intertwined with the fabric of space-time. But to express this idea mathematically, Einstein needed a new language. Classical geometry could not describe a universe where time behaves differently in different places, he turned to the work of mathematicians who had studied curved surfaces and higher dimensional spaces. Their ideas provided the tools he needed to describe a space-time that could warp and bend. As Einstein worked toward this new description, the picture began to crystallize. Matter and energy shape space-time. Space-time, in turn, guides the motion of matter and light. Planets orbit stars not because they feel a pull, but because they are following the natural paths carved into the geometry around them. What appears as a force is the expression of curved space-time. The anomaly in Mercury's orbit was not a mistake. It was a clue pointing toward this deeper truth. With this understanding, a new vision of the universe emerged. The laws Newton discovered were not wrong. They were a powerful approximation that worked wherever space-time curvature was small. But when the curvature grew stronger, Newton's description began to drift away from reality. Einstein's task was not to discard Newton's insights, but to complete them. Gravity was not simply a story about mass. It was a story about the structure of space-time, and time played the leading role. The world was on the verge of seeing gravity in a completely new way. The pieces were falling into place. The anomaly of Mercury, the equivalence principle, the behavior of light, and the strange flexibility of time were all converging. Einstein stood at the threshold of a breakthrough that would transform every field of physics and forever change our understanding of the cosmos. Before the universe revealed its deeper structure, people believed space and time were as simple and reliable as the ticking of a clock or the stretch of a measuring tape. But imagine, for a moment, that these familiar certainties are illusions shaped by a deeper rule. Imagine that two observers, drifting through the darkness between the stars, each carrying identical clocks, could disagree about how much time has passed without either of them being wrong. Imagine that there is no single universal moment shared by the cosmos, no master rhythm keeping order, only local flows of time that shift and tilt depending on how objects move. And imagine that at the heart of everything lies a constant, the speed of light, a value that refuses to change no matter who measures it. What kind of universe emerges when time obeys motion and light obeys no one? Such questions do not simply challenge intuition. They unravel it, thread by thread, until a new vision forms where space and time merge into a single woven fabric. The late 19th century was a turning point. Physicists had woven together electricity and magnetism into a single unified theory that could describe everything from the warmth of a glowing filament to the signals carried along telegraph wires. This theory did something unexpected. It predicted that disturbances in the electromagnetic field would spread at a specific speed, a speed equal to the speed of light. When experimenters began testing this prediction, they ran into a paradox that refused to fade. No matter how they moved or how they arranged their equipment, the speed of light did not shift. According to classical thinking, if you moved toward a beam of light, you should measure it moving faster, and if you moved away from it, you should measure it moving slower. Yet every measurement returned the same answer. The Michelson and Morley experiment is famous because it captured this stubborn result with extraordinary clarity. They built a delicate instrument designed to detect even the slightest change in the speed of light as Earth moved through space. According to expectations, there should have been a measurable difference as Earth drifted through what scientists believed was a background medium called the ether. Instead, the result was null. No change appeared. The speed of light remained the same in every direction. It was as though the universe had imposed a fixed rule that could not be bent or negotiated. This created a quiet crisis. Something had to give. Either the structure of space and time was different from what everyone assumed, or the entire foundation of electromagnetic theory had to be reconsidered. Most scientists resisted the first option because the notion of absolute time and absolute space was so deeply ingrained. It felt natural, almost inevitable. Time ticked forward the same way everywhere. Space stretched identically in all directions. Yet the experimental evidence was whispering a different truth. Einstein approached the puzzle with a different attitude. He was not anchored by the older assumptions. He trusted the laws of electromagnetism because they were supported by a long chain of experiments. If the speed of light remained constant, then perhaps it was time itself that changed. Perhaps time adjusts in order to preserve the constancy of light. This idea was bold, but unavoidable. If two observers in relative motion must both measure light traveling at the same speed, then they cannot agree on the flow of time or the lengths of moving objects. The universe must allow time to stretch or compress, depending on motion. This was the only way to keep the laws of physics consistent for everyone. As soon as this realization solidified, a new landscape of thought began to emerge. Time dilation, the slowing of time for objects in motion, was not an abstract conjecture, but a mathematical consequence of preserving the speed of light. Length contraction, the shortening of objects along the direction of motion, followed naturally from the same reasoning. These effects were small at everyday speeds, which is why no one noticed them in ordinary life. But as objects approached the speed of light, the differences became dramatic. Einstein described this new view with startling clarity in 1905, and the scientific community quickly realized that something fundamental had shifted. Years later, Hermann Minkowski gave this emerging picture its geometric form. He showed that space and time are not separate realms, but interconnected dimensions forming a single entity. In this four-dimensional spacetime, every object traces out a path called a world line. Motion through space affects motion through time, and the geometry of spacetime determines how events relate to one another. Once this idea took hold, the universe could no longer be described as a static backdrop. It became a dynamic stage where time behaves differently for each traveler. Two observers could witness the same sequence of events, yet disagree on the intervals between them, and both would be correct within the framework of spacetime. This vision of reality carried profound implications for gravity. If time itself varies with motion, then gravity cannot simply be a force acting across space. It must be something built into the structure of spacetime, something deeper and more fundamental than a pull between masses. The classical picture that Newton had left behind was no longer sufficient. The hints were there, scattered across experiments and observations, pointing toward a new understanding that would soon reshape physics. The recognition that space and time form a single interconnected fabric did more than resolve a few experimental puzzles. It placed humanity at the threshold of an entirely new worldview. The old intuition, the one that insisted on a shared universal moment and a rigid geometry, began to dissolve. In its place grew a picture where motion sculpts the passage of time and where every observer carries a private rhythm that shifts with speed. The universe was no longer a static container. It had become an active structure with rules far more intricate than anyone expected. Scientists began testing the predictions of this new framework. They sent fast-moving particles through magnetic fields and watched them behave in ways that revealed the stretching of time. Particles that should have decayed quickly lived far longer when accelerated to high speeds. At first, this seemed impossible within the classical picture, but within the new understanding, it made perfect sense. When a particle moves quickly through space, its motion through time slows down. Its internal processes run more slowly compared to those of a stationary observer. The laboratory measurements were precise and consistent. Time dilation was no longer an abstract idea. It was an observable fact. Later, scientists carried clocks on airplanes to test whether motion alone could affect their ticking. When the clocks were compared to identical ones left on the ground, the results lined up perfectly with the predictions of space-time physics. The clocks that had traveled returned slightly out of sync. Their time had flowed differently. The effect was tiny but real, and modern instruments made it impossible to ignore. These experiments confirmed that time is not a universal metronome. Time lives inside space-time and responds to the conditions of motion. These demonstrations began to shift the way physicists viewed gravity itself. If time flows differently depending on motion, then perhaps gravity too is connected to the behavior of time. The idea seemed radical, but the clues were pointing unmistakably in that direction. Newton's force had always worked well for gentle fields, but it did not explain how gravity might behave when time itself changes from place to place. If something as fundamental as the pulse of time can speed up or slow down, then the structure of spacetime must have a role to play in guiding motion. Einstein looked at these clues and sensed that gravity could no longer be explained as an invisible pull. A force that acted across space without delay was incompatible with a universe where signals have a finite speed and where spacetime shapes experience. Instead, gravity had to emerge from the geometry of spacetime. But to arrive at this conclusion, Einstein needed to connect the behavior of space, time, motion, and geometry into a single coherent theory. The unification of space and time was only the beginning. The next challenge was far more ambitious. It required understanding how mass and energy influence the very fabric of space-time. The more Einstein explored the implications of space-time, the more the idea solidified. If events in the universe are woven into this four-dimensional fabric, then motion through this fabric must depend on its geometry. A straight line in space-time is not necessarily a straight line in space. Instead, it is the path that extremizes the interval between two events. In everyday life, objects move along these natural paths without effort. They are not being pulled by an invisible force. They are simply following the structure of space-time itself. This shift in perspective prepared the ground for Einstein's next breakthrough. If time changes with motion, then surely gravity must alter time as well. A clock sitting on the surface of Earth ticks more slowly than a clock on a distant mountain. Although this effect is extremely small, it is measurable. At higher points in the gravitational field, time flows slightly faster. At lower points, it flows slightly slower. These variations are subtle near Earth, but they become dramatic near extremely massive or dense objects. The realization that gravity affects time was a decisive moment in Einstein's thinking. It meant that gravity was deeply tied to the geometry of spacetime. Once this connection became clear, the old notion of a gravitational force began to lose its footing. If the presence of mass changes the flow of time, and if a changing flow of time alters the motion of objects, then gravity might be nothing more than the manifestation of this change. In other words, gravity might be geometry. Einstein had taken the first step. Special relativity had unified space and time. The next step would be even more profound. It would unify gravity with spacetime itself, showing that what people had long called a force was actually something deeper. The next part of the journey would reveal how the geometry of spacetime shapes everything from the orbit of Mercury to the bending of Starlight. The pieces were aligned. The path ahead promised a transformation unlike anything physics had ever seen. Einstein understood that if time could flow differently for observers in motion, then the next great question was unavoidable. How does gravity fit into this new landscape where time and space refuse to behave independently? He began to re-examine every assumption inherited from classical physics. Gravity, in Newton's view, was an invisible influence that acted between distant masses. It had no medium, no messenger, no delay. But this description felt increasingly out of place in a universe where the speed of light limited how information travels. If light requires time to move from one point to another, then gravity too must obey the same constraint. The old picture could not survive in the newly revealed structure of spacetime. To explore this idea, Einstein considered again the relationship between motion and time. If a fast-moving observer experiences slower time than a stationary one, then the geometry of spacetime must respond to motion. But gravity affects motion as well. Objects fall not because they feel a push or pull, but because they naturally follow the easiest path available to them. In ordinary life, these paths seem simple, almost invisible. But in space-time, the geometry could be more complicated. If gravity changes the curvature of space-time, then objects would move along curved paths, even if no force were acting on them. This was the seed of an extraordinary insight. Gravity might be nothing more than the behavior of space-time itself. Einstein imagined a world in which massive objects reshape the space-time around them. A planet or a star would create a sort of depression in the fabric, not a physical indentation, but a change in the way time and space relate. Objects moving nearby would follow the natural paths carved into this structure. They would feel as though they were being pulled, but in truth, they would simply be responding to the geometry. Light, which has no mass, would also follow these curved paths. This meant that light could bend near massive bodies, something Newton's theory could never explain. The bending of light would become a crucial test in the years ahead. The more Einstein explored this idea, the more it aligned with observations. The irregularity in Mercury's orbit was no longer a curiosity. It became evidence that space-time near the lowercase sun is curved in a way Newton's equations could not capture. The orbit of Mercury grazes closer to the lowercase sun than the orbits of other planets, which means it travels through a region where space-time curvature is stronger. A simple force law could not account for this detail, but a geometric theory could. Einstein began to see that if he could describe the curvature of space-time mathematically, he could explain every gravitational effect with remarkable precision. But there was still a missing piece. Einstein needed a way to express the curvature of space-time in precise terms. The ordinary geometry taught in schools was insufficient. He needed a more advanced language, one capable of describing curvature in higher dimensions and relating it directly to the presence of mass and energy. He turned to the work of mathematicians who had developed tools for understanding curved surfaces. Their ideas offered a foundation, but Einstein still needed to reshape them to fit the structure of space-time. Piece by piece, he built the framework that would soon become general relativity. He envisioned space-time as a dynamic entity that could bend, stretch, and ripple. This geometry was not optional. It was the central feature of the universe. Objects move the way they do because space-time is shaped the way it is. Clocks tick the way they do because time itself flows differently within different regions of this geometry. Gravity, as humans experience it, is the expression of a deeper truth. It is the curvature of space-time. By the time Einstein completed this vision, physics had crossed a threshold. Space and time were no longer static, passive ingredients. They had become active participants in the evolution of the cosmos. The unification of space and time was not just an elegant idea, it was a necessary step toward understanding how gravity truly works. And with this unification, Jupiter, Earth, Mercury, Starlight, and even the ticking of clocks all fell into alignment with a single principle. Before Einstein uncovered the true nature of gravity, he spent years wrestling with a question that seems simple, but hides a profound mystery. Why does a falling person feel weightless, even while gravity is acting with full strength? Why does standing still on the ground create the sensation of weight, while plummeting through the air erases it? And what does it mean that a beam of light, which has no mass and no substance to tug upon, bends when it passes near a massive body? These puzzles flicker at the edges of ordinary experience and yet point toward a truth so deep that it would overturn centuries of thinking. If gravity can vanish in free fall and reappear when motion is constrained, then perhaps it is not a traditional force at all. Perhaps gravity is something more subtle, something woven into the behavior of time and space themselves. Einstein often described a moment of clarity that arrived while he imagined a man falling from a rooftop. The man would feel no weight and would float as though drifting in empty space. Every object around him would behave the same way. A dropped key, a loose stone, a scrap of paper would all hover beside him. In that instant, gravity would seem to disappear completely. This was not a mathematical insight. It was a physical truth hiding in plain sight, waiting for someone to pay attention. Einstein called this the happiest thought of his life because it hinted at a symmetry between acceleration and gravity that no one had fully grasped. He realized that if an observer cannot distinguish between free fall in a gravitational field and weightless motion in empty space, then these two situations must share the same underlying physics. This became the equivalence principle, a cornerstone of Einstein's evolving picture. It stated that locally, the effects of gravity and the effects of acceleration are identical. This idea did not come from abstract calculus or complicated formulas. It emerged from an everyday sensation, the realization that falling is indistinguishable from floating. From this thought sprang a cascade of consequences. If you are inside a sealed chamber that accelerates upward, a dropped object will fall to the floor just as it would on Earth. Light shining across the chamber will follow a curved path because the floor rises while the light travels. In an accelerating frame of reference, the beam bends downward. And if the equivalence principle is true, then this bending must also occur in a gravitational field. Light, which was long believed to travel in straight lines, would reveal the influence of gravity without ever feeling a force. It would simply follow the geometry it encounters. This was one of the boldest predictions Einstein ever made. It implied that the path of a beam of starlight skimming past the lowercase sun would curve ever so slightly before continuing onward. This effect was far beyond the precision of 19th century instruments, but it was a direct consequence of the idea that gravity and acceleration share the same nature. Light behaves as though space-time itself is tilted or curved near massive bodies. The bending is a geometric response, not a mechanical pull. Einstein also realized that if acceleration affects the flow of time, then gravity must affect time as well. Imagine a clock placed deep within a gravitational field and another placed farther away. The stronger gravitational environment slows the passage of time for the lower clock. This effect is incredibly small near Earth, but it is real and measurable. It means that time does not flow uniformly throughout the universe. Instead, gravity sculpts the tempo of time the way terrain shapes the flow of water. This understanding led Einstein to a radical conclusion. Gravity must be connected to the curvature of space-time, and the flow of time must be part of this curvature. Newton's force needed no medium, but Einstein's gravity. Before Einstein uncovered the true nature of gravity, he spent years wrestling with a question that seems simple but hides a profound mystery. Why does a falling person feel weightless, even while gravity is acting with full strength? Why does standing still on the ground create the sensation of weight, while plummeting through the air erases it? And what does it mean that a beam of light, which has no mass and no substance to tug upon, bends when it passes near a massive body? These puzzles flicker at the edges of ordinary experience and yet point toward a truth so deep that it would overturn centuries of thinking. If gravity can vanish in free fall and reappear when motion is constrained, then perhaps it is not a traditional force at all. Perhaps gravity is something more subtle, something woven into the behavior of time and space themselves. Einstein often described a moment of clarity that arrived while he imagined a man falling from a rooftop. The man would feel no weight and would float as though drifting in empty space. Every object around him would behave the same way. A dropped key, a loose stone, a scrap of paper would all hover beside him. In that instant, gravity would seem to disappear completely. This was not a mathematical insight. It was a physical truth hiding in plain sight, waiting for someone to pay attention. Einstein called this the happiest thought of his life because it hinted at a symmetry between acceleration and gravity that no one had fully grasped. He realized that if an observer cannot distinguish between free fall in a gravitational field and weightless motion in empty space, then these two situations must share the same underlying physics. This became the equivalence principle, a cornerstone of Einstein's evolving picture. It stated that locally, the effects of gravity and the effects of acceleration are identical. This idea did not come from abstract calculus or complicated formulas. It emerged from an everyday sensation, the realization that falling is indistinguishable from floating. From this thought sprang a cascade of consequences. If you are inside a sealed chamber that accelerates upward, a dropped object will fall to the floor just as it would on Earth. Light shining across the chamber will follow a curved path because the floor rises while the light travels. In an accelerating frame of reference, the beam bends downward. And if the equivalence principle is true, then this bending must also occur in a gravitational field. Light, which was long believed to travel in straight lines, would reveal the influence of gravity without ever feeling a force. It would simply follow the geometry it encounters. This was one of the boldest predictions Einstein ever made. It implied that the path of a beam of starlight skimming past the lowercase sun would curve ever so slightly before continuing onward. This effect was far beyond the precision of 19th century instruments, but it was a direct consequence of the idea that gravity and acceleration share the same nature. Light behaves as though space-time itself is tilted or curved near massive bodies. The bending is a geometric response, not a mechanical pull. Einstein also realized that if acceleration affects the flow of time, then gravity must affect time as well. Imagine a clock placed deep within a gravitational field and another placed farther away. The stronger gravitational environment slows the passage of time for the lower clock. This effect is incredibly small near Earth, but it is real and measurable. It means that time does not flow uniformly throughout the universe. Instead, gravity sculpts the tempo of time the way terrain shapes the flow of water. This understanding led Einstein to a radical conclusion. Gravity must be connected to the curvature of spacetime, and the flow of time must be part of this curvature. Newton's force needed no medium, but Einstein's gravity required a geometry. Matter influences the geometry, and the geometry influences motion. This was the first step toward a new theory that would describe the universe not as a machine built from forces, but as a fabric whose shape dictates how everything moves. Einstein had uncovered a principle that linked gravity and acceleration, time and motion, geometry and light. The theory that would emerge from this insight would explain the orbit of Mercury, the bending of starlight, and the behavior of clocks in gravitational fields. But the idea was still forming, still waiting for the mathematical structure that could express it in full. Einstein could feel the shape of the idea long before he had the mathematics to express it. He sensed that gravity was not a pull between distant bodies, but a reflection of how space-time arranges itself around mass and energy. Yet sensing a truth and proving it are entirely different challenges. He needed a language capable of describing a world where time could slow down, lengths could stretch, and paths of motion could curve without any force acting. The familiar geometry of schoolbooks was too simple. It could describe flat surfaces, straight lines, and gentle curves, but it could not capture the deep structure of space-time that Einstein suspected was responsible for gravity. He began by studying how motion unfolds when no forces act at all. In ordinary life, an object thrown into the air eventually falls because of gravity, but if gravity were removed, the object would drift along a straight path at constant speed. This straight line in space is familiar, but in space-time, the situation is more subtle. A straight path is not defined by visual simplicity, but by the absence of acceleration. Einstein realized that if gravity is not truly a force, then objects falling freely must be following the straightest possible paths in space-time, even though the paths appear curved when viewed in ordinary space. This means the geometry of space-time determines the path of a falling apple, just as it determines the orbit of Mercury or the path of a beam of light near a star. To express this idea mathematically, Einstein needed to understand how curved surfaces behave. He studied the works of mathematicians who had explored the geometry of curved shapes such as spheres and saddles. These shapes defied the rules of flat geometry. Lines that appeared straight were not truly straight. Distances that seemed equal could differ depending on the curvature. Einstein began to imagine how these ideas could be extended into 4 dimensions, where time is as essential as distance. If the geometry of spacetime could bend, then time intervals and spatial distances could stretch or shrink. Objects would move according to this curvature, not because they feel a force, but because the geometry guides them. The equivalence principle continued to illuminate the path forward. If gravity and acceleration are locally indistinguishable, then a gravitational field must mimic the geometric effects of acceleration. An accelerating frame of reference tilts the lines of motion within spacetime. In the same way, a gravitational field must tilt the geometry of spacetime around massive bodies. Einstein realized that this tilt is not a metaphor. It is a literal description of the structure of spacetime. The presence of mass and energy changes how spacetime is shaped. The shapes in turn dictate how objects move. Everything from dust particles to planets to beams of light follows these shapes naturally. This insight explained why gravity can appear both strong and gentle. Near dense objects, the curvature of spacetime becomes steep, causing rapid changes in the paths of nearby objects. Far away, where the curvature smooths out, the effects of gravity weaken. Newton's laws had captured this behavior with impressive accuracy, but they had offered no explanation for why it should occur. Einstein saw the deeper reason. Newton's inverse square law emerges naturally from the geometry of spacetime around massive bodies. The familiar force law was not fundamental. It was an approximation to a more profound geometric truth. Einstein then examined the flow of time more closely. If gravity affects time, and if time is part of spacetime, then time must curve along with space. A clock deeper in a gravitational field runs slowly, because the geometry of spacetime is stretched in a particular way near massive objects. A clock higher up runs faster because spacetime is less distorted there. The difference is minute on Earth, but becomes dramatic near extremely dense bodies such as neutron stars. Time itself bends under the influence of gravity. This bending is not symbolic, it is measurable, it is physical. It is the reason why global positioning systems must account for gravitational time differences, or else their signals drift and produce errors. By this point, the pieces of Einstein's vision were clear. Gravity is geometry. Time is part of this geometry. Mass and energy sculpt the geometry. Objects move according to the shape of the geometry. All that remained was to construct the mathematical framework capable of capturing these relationships precisely. The task would take years of intense thought, failed attempts, and flashes of inspiration. But Einstein had already crossed the conceptual boundary. He no longer viewed gravity as a force. He saw it as the natural behavior of space-time. The stage was prepared for the final leap. The bending of light, the drifting orbit of Mercury, the slowing of clocks, and the sensation of free fall were no longer separate puzzles. They were pieces of a single deeper theory waiting to be written down. Einstein pressed deeper into the idea that gravity must be the expression of curved space-time. But turning this vision into a functioning theory proved far more difficult than the initial insight. He spent years trying to translate intuition into equations that could describe how space-time bends and how matter shapes that bending. During this period, he experienced both exhilarating breakthroughs and long stretches of frustration. He knew the answer depended on finding a way to relate the distribution of mass and energy to the curvature of space-time, but no existing mathematical tool could do this cleanly. He needed a new kind of geometry, one capable of describing how distances, angles, and intervals behave in a curved, four-dimensional arena. He turned again to the work of mathematicians who had explored complex geometries long before physicists realized they were needed. Bernhard Riemann had developed a set of ideas for describing curved surfaces, ideas that included tensors, objects that could encode how distances change from point to point on a curved surface. Einstein realized that tensors could do more than describe curved landscapes. They could describe curved space-time. This was the breakthrough he needed. With tensors, he could begin to express how space-time stretches and twists around mass and energy. Yet even with this mathematical, imagine standing on a quiet hillside at night while the stars drift above you. The ground beneath your feet feels solid, unmoving, and predictable, yet the space around you is anything but simple. If you could peel back the surface of ordinary experience, you would find something astonishing. Space is not a rigid backdrop. Time is not a steady rhythm. Together they form a pliable fabric that bends, stretches, and twists in response to matter and energy. The planets circling the lowercase sun, the arcs traced by distant comets, even the path of the light reaching your eyes, all follow routes shaped by this invisible structure. What seems flat is curved, and what seems still is alive with hidden motion. When Einstein stepped into this realm, he discovered that gravity is not a force at all. Gravity is geometry. To appreciate this idea, picture a traveler moving through the universe with no forces acting on them. In classical physics, that traveler would drift in a straight line at constant speed. But in the language of space-time, straightness means something deeper. A straight path is the one that preserves the natural interval of space-time, the path that requires no effort, no acceleration. This path is called a geodesic. On a flat table, a geodesic is a straight line. On a curved surface, such as the skin of a sphere, geodesics become great circles. They are still straight in the geometric sense, even though they appear curved when glanced at from a different perspective. Einstein realized that planets, moons, and even beams of light follow geodesics through space-time. Their motion is not commanded by a force. It is guided by the shapes carved into the fabric of reality. This understanding meant that the curvature of space-time must reflect the presence of mass and energy. A massive object, such as a star or planet, does not pull on surrounding objects. Instead, it reshapes the geometry near it. An object moving through this region follows the geodesics determined by that geometry. When you watch a planet orbit the lowercase sun, you are witnessing a body gliding through curved space-time, not circling under the influence of a mysterious pull. When a stone falls to Earth, it is not being dragged downward by an invisible hand. It is simply following the path that space-time makes easiest. The ground stops it, not gravity. Free fall is the purest motion. Weight is resistance. To construct this explanation in a mathematical form, Einstein needed to describe exactly how space-time curves. Curvature is not something you can see directly. It must be defined in terms of how distances and intervals behave. On a curved surface, the shortest path between 2 points is not the straight line you would expect. Angles add in unusual ways, and triangles refuse to follow the familiar rules. Einstein borrowed these ideas from the geometry of curved surfaces and extended them into four-dimensional space-time. He found that curvature could be expressed with a mathematical object that captured how intervals change. This object allowed him to describe how space-time bends around massive bodies and how objects trace geodesics through that curvature. The astonishing part of this vision is not that space-time can bend, but that time itself is part of this bending. Time does not flow uniformly in this geometric world. Near massive objects, the structure of space-time stretches in such a way that time slows. Farther away, where curvature is gentler, time speeds up. This variation is not merely philosophical, it is measurable. Clocks placed at different heights in a gravitational field tick at different rates. Light climbing out of a gravitational well loses energy and stretches into longer wavelengths. These effects arise naturally when time is treated as one dimension of a curved space-time. Einstein also understood that the curvature of space-time could propagate. If a massive object were to move or accelerate, it would disturb the geometry around it. These disturbances would ripple outward like waves on a pond. These gravitational waves travel at the speed of light and carry information about their sources. Although Einstein predicted them early in his work, he doubted whether they could ever be detected. The curvature of space-time is subtle, and its ripples even more so. Yet the universe holds surprises for anyone willing to look closely enough. By the time Einstein finished constructing this framework, gravity had been transformed from a force into a property of the universe itself. The orbits of planets, the fall of objects, the bending of light, and the flow of time all followed from the shape of space-time. The theory was elegant, but elegance alone is not enough. It needed to match reality. The bending of starlight during an eclipse, the anomaly in Mercury's orbit, and the redshift of light in a gravitational field would soon test whether this geometric vision was correct. Einstein had built a breathtaking idea, but the true power of the theory emerged when he explored how the geometry of space-time responds to the presence of matter. He needed a rule that would specify how much curvature appears around a given distribution of mass and energy. This was not a simple question. The curvature had to adjust smoothly, remain consistent with the behavior of light, and return to Newton's familiar laws in the gentle environments of everyday life. The task required a delicate balance. Too much curvature would yield orbits that spiraled wildly. Too little curvature would fail to explain the motion of Mercury or the bending of starlight. Einstein spent years refining the relationship between matter and geometry, until he finally arrived at an equation that could express the entire structure of gravity with astonishing clarity. This equation revealed that the curvature of space-time at a point depends on the density and flow of energy at that same point. Mass, motion, pressure, and even radiation contribute to this curvature. Nothing with energy is excluded. The geometry is not sculpted only by stars or planets. It is shaped by every type of energy in the cosmos. Even a beam of light contributes to curvature, although the effect is extremely small. This universality gives gravity its unique character. All forms of matter and energy influence space-time, and all objects follow the geometry that results. Gravity does not discriminate. Its reach extends everywhere. Einstein wanted more than mathematical consistency. He wanted physical meaning. He imagined space-time as a living landscape where mass and energy press into the fabric, altering its shape. You can picture a massive object as creating a valley in space-time, and objects around it naturally roll along the slopes of that valley. But this image, while useful, does not capture the true depth of the idea. The curvature is not a bending in some higher space. It is an intrinsic feature of space-time itself. There is no outside surface to lean on, no hidden dimension where the curve appears. The geometry lives inside the universe, and everything within it moves according to that geometry. This shift in perspective becomes even more profound when you consider the motion of light. Light does not slow down or speed up because of gravity. It always travels at the same speed, but the geometry it passes through may be curved. As a result, light follows the geodesics of space-time. When it passes near a massive star, its path bends because the geometry bends. This bending is subtle but real. It means that light is not merely a messenger moving through space. It is a participant in the geometry, revealing through its trajectory the hidden shape of space-time. In this sense, light becomes a probe, a tool for mapping curvature with exquisite precision. The realization that time curves just as space curves adds another layer of wonder to the theory. If you could place identical clocks at different distances from a massive body, they would tick at different rates. The closer clock would run more slowly because the curvature near the mass forces time to stretch. This stretching changes everything. It alters the behavior of atomic processes. It shifts the frequency of light climbing out of a gravitational field. It even affects the paths of satellites circling Earth. In everyday life, these effects are small, but the universe contains objects where gravitational curvature becomes extreme. Near neutron stars or the event horizons of black holes, the stretching of time becomes dramatic. Time can slow to a crawl compared to the flow experienced far away. This is not an illusion. It is the geometry of the universe acting on the fabric of time. Einstein saw that if gravity is geometry, then the motion of all objects, from planets to photons, is the natural outcome of that geometry. A planet orbiting a star is not bound by a force, but is following the easiest path through curved spacetime. A stone falling to the ground is obeying the same rule. The ground stops it from following its natural geodesic, producing what we call weight. Free fall is nothing more than moving along the unforced path set by spacetime. This interpretation dissolves the mystery of action at a distance. There is no influence that must travel. The curvature already exists, and objects respond to it instantly because it is not a separate entity. It is the arena itself. The deeper Einstein pushed this idea, the more connections he uncovered. The tides that sweep across Earth are shaped by the geometry created by the lowercase sun and the moon. The precession of spinning objects is influenced by the curvature through which they move. Even the stability of galaxies owes something to the collective geometry produced by countless stars. The theory had grown so broad and so powerful that it touched nearly every domain of physics. But the true test of its value would come from the sky, from the light of distant stars bending gently as it passed near the lowercase sun during a rare moment when observers on Earth could measure it. The mathematics was complete. The ideas were coherent. The predictions were bold. Now the universe itself would determine whether Einstein had uncovered its true design. Einstein had transformed gravity into a geometric phenomenon, but theory alone could not secure its place in the scientific world. Nature would need to reveal its agreement through observation. The first and most dramatic test came from a phenomenon that had long intrigued astronomers, but had never been fully understood: the way light behaves when it travels near a massive object. According to Einstein's geometry, the lowercase sun should bend the path of starlight, passing close to its surface. The bending would be small, far too subtle for the unaided eye, yet large enough to be detected during a total solar eclipse when the lowercase sun becomes briefly hidden and the stars near its edge can be observed. Einstein calculated the angle of this bending and found a value that differed from Newton's purely mechanical prediction. If nature returned Einstein's number instead of Newton's, it would mean the universe truly follows the curvature of spacetime. Astronomers waited for the alignment of a rare total eclipse, and in 1919, expeditions from Europe traveled to distant locations to capture the moment. Clouds threatened the observations, and equipment struggled against the environmental challenges, but the data that emerged revealed something extraordinary. The starlight appeared shifted by exactly the amount predicted by Einstein. His theory had withstood the test. The bending of light, once unmeasurable, had now become a message written across the sky, confirming that the universe curves and that light traces its contours. This event did not simply validate a mathematical idea. It changed the course of scientific history. Newspapers around the world declared that Newton's universe had given way to Einstein's. Yet the bending of light was only the beginning. Einstein turned his attention to the motion of planets. The orbit of Mercury, which had puzzled astronomers for more than a century, was now understood as a natural consequence of space-time curvature near the lowercase sun. The precession of Mercury's orbit emerged automatically from Einstein's equations. This explanation required no hidden planets, no adjustments, and no speculative forces. It was the result of geometry alone. Another prediction concerned the shift in the wavelength of light escaping from a gravitational field. If time runs more slowly deeper in a gravitational well, then light climbing out must stretch into longer wavelengths. This phenomenon, known as gravitational redshift, would later be confirmed in laboratory experiments by measuring the subtle changes in wavelength as light moved between points at different gravitational potentials. The precision of these measurements left no doubt. Gravity alters time, and time alters the energy of light. Einstein also predicted a phenomenon known as frame dragging, in which rotating bodies twist the space-time around them. This effect is far too weak to observe in ordinary daily experience, but it can be measured with sensitive satellites orbiting Earth. Generations after Einstein proposed the idea, experiments confirmed that Earth does indeed drag space-time slightly as it spins. This subtle twist is another signature of the geometric nature of gravity. The ultimate triumph of this geometric vision came with the detection of gravitational waves. Einstein had predicted that accelerating masses should generate ripples in spacetime that propagate outward at the speed of light. These ripples are unimaginably faint, and for decades many doubted they could ever be measured. But in the 21st century, instruments designed with exquisite sensitivity observed the passing of gravitational waves produced by colliding black holes. These waves carried information about the distant event, revealing the shapes and masses of the objects involved. They proved that the geometry of spacetime can ripple, vibrate, and carry energy across the universe. By the time these tests accumulated, Einstein's theory had evolved from a bold proposal into one of the most thoroughly verified scientific frameworks ever created. Yet the true power of the theory lies not only in its accuracy, but in its unification of phenomena that once seemed unrelated. The fall of an apple, the orbit of Mercury, the bending of starlight, the ticking of clocks, and the ripples of cosmic collisions all emerge from the same principle. Space-time has geometry, and that geometry determines motion. Einstein had revealed a universe where gravity is no longer a mysterious force, but the expression of a deeper structure. The curvature of space-time governs everything from the smallest step you take to the largest motion of galaxies. This geometric view does not diminish the wonder of gravity, but enhances it, revealing a universe shaped by the silent influence of curved time and space. Every moment of your life unfolds along a path carved into the cosmic fabric, and every motion is a dialogue between matter and geometry. Before anyone could accept that gravity is the curvature of space-time, the universe itself needed to speak. A theory so bold demanded evidence drawn not from imagination, but from the sky, from the hidden precision of clocks, and from the delicate fingerprints left on light as it travels through the cosmos. Einstein had offered a radical idea, one that replaced an invisible force with a living geometry. But such an idea could not stand on elegance alone. It needed a moment when nature would reveal her preference, choosing between the straight lines of Newton's universe and the curved space-time of Einstein's. That moment would come from Starlight. The question was simple but profound. Would the light from distant stars passing near the lowercase sun bend by the amount predicted by Einstein's equations? Or would it bend by the smaller amount suggested by Newton's picture? The answer, hidden in a thin slice of sky visible only during a total eclipse, would decide the fate of both worlds. To understand why the bending of starlight matters, imagine light as a traveler that knows only one rule. It must always move at the same speed through space-time. It does not choose its path. It follows the geometry it encounters. If space-time curves near a massive object, then the path of light will curve with it. Einstein predicted that this bending should be twice as large as the value implied by Newton's ideas. The difference arose because Einstein recognized that both space and time curve near massive bodies. Newton accounted only for space. If Einstein was right, then starlight brushing past the lowercase sun would veer slightly inward before continuing on its way. During the daytime, this effect cannot be seen. The lowercase sun overwhelms the stars with its brilliance. But during a total eclipse, the sky briefly darkens, and stars scattered near the darkened disk of the lowercase sun become visible. Their shifted positions, recorded on photographic plates, would reveal the curvature of space-time. The world waited. In 1919, expeditions led by Arthur Eddington set sail to distant locations where a total eclipse would be visible. The effort was immense. Photographic instruments had to be transported across oceans and set up in harsh conditions with no guarantee of clear skies. Clouds threatened to erase months of preparation. Yet when the eclipse finally arrived and the plates were developed, the results were unmistakable. The positions of the stars were shifted by exactly the amount predicted by Einstein. The bending of light matched the curvature calculated from his field equations. In that moment, the universe whispered its first confirmation. Gravity was geometry. Time and space were one. The announcement echoed around the world. Newspapers declared the overthrow of Newton and the triumph of a new vision. Scientists, once cautious, now saw that Einstein had not merely offered a novel interpretation, he had revealed a truth hidden in the very behavior of light. But Starlight was only the first messenger. Other tests waited in the wings, each ready to reveal another facet of spacetime's geometry. The next great confirmation came from Mercury, the small and swift world closest to the lowercase sun. For decades, astronomers had puzzled over its orbit. The point of Mercury's closest approach to the lowercase sun shifted over time in a way Newton's equations could not fully explain. The discrepancy was tiny, only about 43 arc-seconds per century, but it persisted no matter how carefully the calculations were refined. Einstein applied his new geometric theory to the orbit of Mercury and discovered that the curvature of spacetime near the lowercase sun naturally produced the missing drift. The anomaly vanished. The orbit aligned. The equation worked not only for Starlight, but for planets as well. Yet another clue came from the passage of time itself. If gravity affects time, then a clock stationed deep in a gravitational field should tick more slowly than one placed at a higher location. This prediction, subtle and counterintuitive, was tested decades later in a laboratory experiment known as the Pound and Rebka measurement. By sending light up a tower and detecting the shift in its frequency, scientists confirmed that gravity stretched time exactly as Einstein had predicted. Light climbing upward lost a tiny bit of energy, revealing the difference in the flow of time between the top and bottom of the tower. Time was no longer absolute. It bent beneath the weight of gravity. Einstein's predictions extended even further. If clocks in different gravitational environments drift relative to one another, then identical clocks flown around Earth on aircraft should return with different elapsed times. This experiment was performed with atomic clocks carried aboard airplanes. When the clocks were compared after the flights, they showed precisely the differences predicted by general relativity. Gravity and motion had reshaped the flow of time. The effect was small but real, and modern satellites must correct for these variations to maintain accuracy. Without this correction, global positioning systems would drift wildly, rendering them useless. Each test strengthened the geometric view of gravity. Each measurement revealed that space-time behaves exactly as Einstein described. But the universe held one more dramatic confirmation, a phenomenon so subtle that even Einstein doubted it might ever be detected. Rotating bodies, he argued, should twist the space-time around them, dragging it slightly as they spin. This frame-dragging effect would be unimaginably faint near Earth, but detectable with the right instruments. After decades of planning, a satellite experiment succeeded in measuring the tiny twist produced by Earth's rotation. The result confirmed yet another prediction of space-time curvature. These experiments transformed general relativity from a bold idea into a confirmed description of the cosmos. The bending of starlight, the precession of Mercury, the slowing of time, the stretching of light, and the twisting of space-time all pointed to the same conclusion. Gravity arises from the geometry of the universe. Mass and energy shape space-time, and space-time guides the motion of everything within it. The confirmations of Einstein's theory did more than validate a new picture of gravity. They revealed that the universe contains layers of structure far richer than anyone had imagined. Each experiment acted like a lantern, illuminating a small corner of the geometric landscape that surrounds us. But the deeper investigators looked, the more they realized that gravity does not merely shape the motion of planets and the behavior of light. It reaches into the heart of matter, alters the tempo of time, and influences the unfolding of cosmic events across billions of years. The bending of starlight during the eclipse of 1919 had been dramatic, but it was only the first whisper. More tests would come, growing in sophistication, revealing the power of the theory through the most delicate and surprising measurements. One of the earliest clues arrived not from the vastness of space, but from the tiny rhythms of atoms. Scientists knew that certain atomic processes depend on time at the smallest scales. If gravity slows the flow of time, then atomic transitions should reveal the difference. The Pound and Rebka experiment provided the first solid evidence by showing that light sent upward in Earth's gravitational field shifted in frequency as though it had lost energy while climbing out of a gravitational well. This shift was extremely small, almost unimaginably so, but precise measurements captured it clearly. It reflected the stretching of time itself. If time were uniform, the experiment would have produced no change. Instead, it revealed that time bends under gravity, confirming one of the most profound consequences of Einstein's theory. The influence of gravity on time took a dramatic turn when scientists flew extremely stable clocks around Earth. The idea was simple. If gravity slows time, and if motion also slows time, then clocks flown eastward and westward around the globe should accumulate different amounts of time compared to clocks that remained stationary. The results were remarkable. The airborne clocks returned slightly but unmistakably out of sync. They ticked at rates predicted by the combined effects of motion and gravity. This meant that time is not an indifferent backdrop. It is a dynamic variable, responsive to movement and curvature. Every tick of every clock in the universe participates in this shifting flow. This revelation did more than confirm Einstein's equations. It changed the way scientists understood technology. The clocks orbiting Earth aboard global positioning satellites are affected by both their motion and their altitude. They run faster than clocks on Earth because they sit higher in the gravitational field and experience less curvature in space-time. If these differences were ignored, satellite signals would drift and fail to align with the positions they are meant to guide. General relativity is therefore not only a cosmic principle, it has become a practical tool woven into the functioning of modern society. Every time a device calculates a position using signals from orbit, it performs a small tribute to Einstein's geometry of time. While clocks and satellites tested the behavior of time, another family of tests explored how gravity influences the motion of objects in strong or changing fields. Einstein's theory predicted that a spinning planet should slightly twist the space-time around it, producing a subtle dragging effect. This prediction seemed almost unreachable for decades, too small to be detected directly. But technology marched forward, and eventually scientists launched a satellite equipped with ultra-precise sensors capable of measuring minute changes in orientation as it orbited Earth. The results matched Einstein's predictions. Earth's rotation does indeed twist space-time ever so slightly, as though the planet drags the fabric of the universe around with it. This effect, minute though it is, offers yet another glimpse into the geometric nature of gravity. By now, the evidence had grown so compelling that general relativity stood firm as the guiding framework for understanding gravity. Yet the universe held one more confirmation of extraordinary significance. Einstein had predicted that whenever massive objects accelerate, they should generate ripples in space-time that travel outward at the speed of light. These gravitational waves would be faint, passing through matter with almost no resistance. For decades, their detection seemed impossible, but deep in the quiet cavities of advanced detectors, scientists built instruments designed to sense the tiniest stretching and squeezing of space-time. In 2015, a signal arrived. Two black holes had spiraled into one another more than 1 billion light-years away, and the collisions sent waves rippling across the universe. These waves washed through Earth and shifted the lengths of the detector arms by less than the thickness of a proton. Yet the instruments registered the change. The shape of the signal matched exactly the predictions of Einstein's equations. It was a moment as historic as the 1919 eclipse. The universe had spoken again, this time through the trembling of space-time itself. The collection of confirmations formed a pattern too precise to ignore. Light bends as predicted. Time stretches as predicted. Orbits shift as predicted. Clocks drift as predicted. Space-time ripples as predicted. Over and over, nature revealed her agreement with the geometric description that Einstein had uncovered. General relativity stood not as a clever reinterpretation of old ideas, but as a new language for the universe, one that described gravity as the shape of space-time rather than a force acting across space. Every test reinforced the same conclusion. The geometry of space-time is real. It influences matter. It guides light. It sculpts time. And above all, it expresses what gravity truly is. The growing tapestry of evidence began to reveal something remarkable. Each test of Einstein's theory illuminated a different corner of the universe, yet all of them pointed to the same geometric truth. What had once been thought of as an invisible force acting mysteriously across empty space now appeared as the natural expression of a curved and dynamic space-time. The bending of starlight and the drifting orbit of Mercury had provided early signs, but as decades passed, scientists discovered that the geometry of gravity reaches into realms far stranger and more extreme than anyone in the early 20th century could have imagined. One of the most subtle proofs came from the way particles behave when they move at high speeds. Near the speed of light, the predictions of special relativity and general relativity blend together. Particles experience time differently depending on their motion and position in a gravitational field. Experiments in particle accelerators showed that unstable particles, which decay quickly when at rest, live longer when traveling at high speeds. This effect is not caused by any mysterious force. It is caused by time itself stretching. The particles' internal processes slow as they move through space-time. Their extended lifetimes match perfectly with Einstein's predictions and stand as a quiet but powerful confirmation that time is not absolute. It is shaped by motion and gravity together. Meanwhile, astronomers looked for evidence of gravitational lensing, the bending of light not just near the lowercase sun, but throughout the cosmos. If massive objects curve space-time, then galaxies or clusters of galaxies should act like natural lenses, magnifying and distorting the light of objects behind them. Telescopes soon revealed arcs, rings, and stretched patterns of distant galaxies, all created by this cosmic lensing. These shapes were not artistic accidents. They were geometric signatures. Each distorted arc traced the curvature of space-time, allowing scientists to map invisible mass and explore regions that would otherwise remain hidden. In this way, lensing became not merely a test of general relativity, but an essential tool for studying the structure of the universe. The idea that light bends and stretches under the influence of gravity also reshaped the way scientists study the cosmos. Light climbing away from dense regions loses energy, shifting into longer wavelengths. This gravitational redshift can be observed in the spectra of stars, especially those with strong gravitational fields. The exact amount of redshift predicted by general relativity matches the measurements captured by observatories around the world. Even the tiny gravitational differences between mountaintops and valleys influence the wavelengths of light and the ticking rates of clocks, proving that time flows differently across even modest changes in altitude. Yet perhaps the most profound confirmations came from the study of extreme astrophysical environments. Einstein's theory predicted the existence of black holes, regions where space-time becomes so curved that not even light can escape. For decades, these objects were theoretical, supported indirectly by the energy of collapsing stars and the motion of nearby objects. But as telescopes improved, evidence grew stronger. Stars near the center of our galaxy traced tight loops around an invisible mass millions of times greater than that of Earth's lowercase sun. Their motion could only be explained if space-time around them was shaped by a supermassive black hole. Later, in 2019, the Event Horizon Telescope produced the first image of a black hole's shadow. It revealed a bright ring of light orbiting a dark center, exactly as predicted by general relativity. The image was not a simple photograph. It was a map of space-time itself, captured in the glow of matter swirling at the edge of the event horizon. Gravitational waves added even more weight to this picture. The ripples detected in 2015, and in many events since then, showed that space-time behaves like a medium capable of trembling under the influence of distant cataclysms. The shapes of these waveforms carry information about their sources, confirming again and again that the geometry of space-time governs the lives and deaths of massive bodies. Every detection reinforces the same conclusion. The universe is not built on forces that act across distance. It is built on a fabric whose curvature directs everything that moves. Each of these confirmations, whether drawn from laboratory clocks, distant galaxies, particle beams, or the silent tremors of black hole mergers, strengthens the same idea. General relativity is not a theory that explains one or two phenomena. It is a framework that shapes the entire universe. It reveals that time flows at different rates in different places, that light bends not because of a pull, but because the geometry demands it, and that the paths of planets and stars are written into the very shape of space-time. No force reaches across emptiness. Instead, matter and energy sculpt the geometry, and the geometry guides everything within it. By the end of the 20th century and into the present century, the evidence had grown overwhelming. The universe had provided its verdict. Gravity is geometry. The curvature of space-time is not an abstract idea. It is a physical reality that influences everything from the motion of galaxies to the functioning of your handheld devices. The bending of starlight during an eclipse was the beginning. The trembling of space-time under the passage of gravitational waves was a confirmation a century in the making. Before the universe reveals its most extreme secrets, it often offers gentle hints. A shift in starlight here, a slowing of a clock there, a whisper of curvature woven into the motion of planets. But beyond these subtle signs lies a realm where the geometry of space-time becomes so intense that ordinary intuition breaks apart. Imagine a place where time itself stretches towards stillness, where light bends inward as though reluctant to escape, and where motion becomes trapped in loops carved by gravity so strong that even the fastest signals the universe allows cannot break free. These places are not myth nor speculation. They arise directly from Einstein's equations, predicted before anyone had the tools or observations to confirm them. They are black holes, the most extreme expressions of curved space-time, and their existence forces a deeper question. What happens to time, space, and motion when gravity becomes almost infinitely strong? The story began quietly in 1916, when Carl Schwarzschild, a physicist serving on the front lines of the First World War, solved Einstein's field equations for the simple case of a spherical mass. His solution revealed something startling. If enough mass is compressed into a sufficiently small region, the curvature of space-time becomes so severe that a boundary forms. This boundary, now known as the event horizon, marks the point beyond which escape becomes impossible. Inside this region, all paths lead inward. Even light, which always travels at the same speed, cannot find a route that carries it back out. The event horizon is not a physical surface. It is a limit woven from geometry. It is the place where time and space switch roles in a way that defies normal experience. To an outside observer, the approach to this boundary unfolds in slow motion. Imagine watching an object fall toward a black hole. As it moves closer, the light it emits becomes stretched into longer and longer wavelengths. The ticking of a clock attached to the falling object slows compared to your own. Eventually, as the object approaches the event horizon, its light fades and its time appears to freeze. It never quite reaches the boundary from your perspective. It simply becomes dimmer, redder, and slower until it fades from sight entirely. This is not a trick of distance or obscurity. It is a direct consequence of the way space-time curves near a black hole. Time itself becomes so distorted that from the outside, it almost stops. But from the viewpoint of the falling object, the journey is different. time flows normally for the traveler, who crosses the event horizon without noticing anything special at the moment of crossing. The divergence between these perspectives reveals the fundamental nature of curved spacetime. Each observer experiences time locally, and those local experiences can differ radically depending on the geometry they inhabit. The black hole does not destroy time. It reshapes it into something deeper and stranger than any familiar notion. The flow of time near the horizon becomes inseparable from the structure of space itself. For decades, black holes remained largely theoretical. Their extreme nature made them difficult to detect directly. But as astronomers studied the universe more closely, evidence grew that these objects must exist. Some stars move as though pulled by an unseen giant. Gas swirling around invisible centers of mass reaches astonishing temperatures, radiating intense light before disappearing into darkness. These clues hinted at regions of spacetime where gravity had tightened into the shape predicted by Schwarzschild's solution. The true power of Einstein's geometry reveals itself as one approaches the event horizon. Spacetime curves downward like an infinitely deep well, and the geometry becomes so steep that the natural paths of motion always lead inward. Even beams of light follow this rule. They do not curve because of a force. They curve because spacetime itself is bent in such a way that every available route angles inward. A photon launched outward from just inside the event horizon cannot climb the steep wall of geometry. It is carried inward because all future paths lead toward the center. This behavior underscores a simple but extraordinary truth. Black holes are not objects in space. They are regions of spacetime where the geometry becomes radical. Scientists also realized that if black holes exist, they can merge. When two massive black holes spiral around each other, they distort spacetime violently, sending waves across the cosmos. These gravitational waves, predicted by Einstein, would be faint by the time they reached Earth, but detectable with instruments sensitive enough to measure changes smaller than the width of a proton. For most of human history, such sensitivity seemed impossible. Yet the universe does not alter its behavior to suit human expectations. It continues to tell its story, waiting for instruments that can hear it. As the idea of black holes matured, so did the understanding that these objects are not exotic exceptions. They are natural outcomes of the universe's evolution. When massive stars exhaust their fuel, they collapse under their own gravity. If the mass is great enough, no known force can stop the collapse. The space-time around the core tightens until an event horizon forms, and the star becomes a black hole. These remnants scatter throughout galaxies like seeds of darkness, anchoring stellar regions with their immense gravitational influence. Some black holes grow by consuming gas, dust, and even other stars. Others form from the mergers of earlier black holes. Over time, they can become millions or even billions of times more massive than the lowercase sun, shaping the centers of galaxies. In exploring these objects, scientists have begun to see that black holes are more than regions of intense gravity. They are laboratories where spacetime reveals its most dramatic behavior. They show that the flow of time is not absolute. They show that light is not immune to the curvature of the universe. They demonstrate that geometry can become so extreme that the familiar laws of motion transform into something richer and more complex. Black holes are not cosmic anomalies. They are the ultimate consequence of general relativity, the unavoidable outcome of Einstein's curved spacetime. The deeper scientists ventured into the study of black holes, the more the universe revealed that these objects are not merely regions of extreme gravity, but gateways into the very architecture of spacetime. They stand as cosmic amplifiers, taking the gentle curvature that shapes planetary orbits and stretching it to its most dramatic form. If spacetime around Earth bends gently enough that clocks differ by fractions of a second, then spacetime near a black hole bends so sharply that time itself approaches stillness. This is not a metaphor. It is a measurable, mathematical, and observational truth, one that unfolds with perfect consistency from Einstein's equations. To understand why time slows near a black hole, imagine climbing a steep hill of geometry. In the world described by general relativity, time flows along the contours of space-time. Near Earth, these contours slope gently, so time flows almost uniformly. But near a black hole, the slope becomes so steep that climbing out requires immense effort, even for light. When light attempts to escape the gravitational well, it loses energy. Its wavelength stretches, shifting it to redder and redder colors. This gravitational redshift grows stronger as you approach the event horizon. For an outside observer, the light from someone falling toward the horizon becomes dimmer, slower, and stretched until it fades entirely. Time for the falling observer appears to slow, drawn out by the steepness of the space-time structure. Yet for the falling observer, nothing unusual happens at the horizon itself. Time flows normally within their own frame. This paradox reveals one of the most profound truths of Einstein's geometry. Time is not universal. It is local, shaped by the curvature of space-time in the immediate environment. Two observers can pass through entirely different flows of time, each correct within their own experience. It is only when their perspectives are compared that the divergence appears. The differing rates of time are not illusions. They are consequences of the geometry through which each observer moves. The extreme environment near a black hole also transforms the behavior of matter. Gas spiraling toward the event horizon collects in a swirling, luminous disk. Friction and magnetic fields heat this gas to extraordinary temperatures, causing it to radiate across the electromagnetic spectrum. Observatories capture these emissions, especially in X-ray wavelengths, and from them astronomers can infer the presence of a black hole. The gas does not glow because the black hole pulls on it with an invisible force. It glows because gravitational curvature accelerates the gas to incredible speeds, heating it as it spirals inward. The light radiated from this process becomes one of the strongest signatures that a black hole is present. Some black holes are small, formed from the collapse of massive stars. Others grow monstrous, becoming millions or billions of times more massive than the lowercase sun. At the centers of galaxies, including our own, evidence points to the presence of supermassive black holes. Stars near these giants move at extraordinary speeds, tracing tight loops that cannot be explained by any ordinary mass. By tracking the orbits of these stars, astronomers have measured the immense central object in our galaxy with remarkable precision. Its mass is equivalent to millions of lowercase suns, yet it occupies a region no larger than our solar system. Nothing other than a black hole can account for such density. Black holes also reveal themselves through the jets they produce. As gas spirals inward, some of it becomes channeled along magnetic field lines and launched outward at nearly the speed of light. These jets stretch across light years, sometimes even hundreds of thousands of light years, slicing through interstellar and intergalactic space. Such jets do not emerge from the event horizon itself, but from the region around it, where the space-time curvature and magnetic fields are extreme. Observations of these jets confirm that black holes influence not just their immediate surroundings, but entire galactic ecosystems. The deeper scientists looked, the more they realized that black holes are not merely destructive objects. They are engines of cosmic evolution. By shaping the motion of gas and stars around them, they regulate star formation within galaxies. They anchor galactic centers, influence the growth of galaxies over billions of years, and generate the most powerful events in the cosmos. Their existence, once doubted, has become one of the most robust pillars of modern astrophysics. Yet perhaps the most spectacular confirmation of their reality came from the detection of gravitational waves. When two black holes spiral inward and merge, they create a colossal disturbance in space-time. The resulting waves ripple outward like tremors on a cosmic pond. When these waves pass through Earth, they stretch and compress space by an amount smaller than a proton's width. Detecting such tiny distortions requires extraordinary precision. In 2015, the first detection of these waves proved that black holes not only exist, but collide, merge, and reshape space-time in ways Einstein had predicted a century earlier. Each detection since then has unveiled a new chapter in the lives of black holes. Scientists can hear, in a sense, the final moments before two black holes fuse. The rising pitch of the gravitational wave signal, the sudden quiet after the merger, and the lingering vibrations of the resulting black hole match Einstein's equations with stunning accuracy. It is as though the universe is speaking in the language of geometry, and humanity has finally built instruments sensitive enough to listen. Black holes stand as the strongest evidence that gravity is geometry. They reveal how space-time can fold, tighten, stretch, and nearly halt the flow of time itself. They are not cracks in the universe, but natural features of its design, places where the curvature of space-time reaches its most dramatic form. In their shadowed boundaries, time slows. Light bends inward, motion becomes trapped, and through them, the universe demonstrates the full power of Einstein's theory. Even as black holes grew from theoretical curiosities into established astrophysical realities, they continued to challenge human intuition. Their very existence demanded a deeper understanding of the ways space-time behaves under the most extreme conditions. Each new observation seemed to peel back another layer of mystery, revealing that the geometry shaping these objects is more intricate than even Einstein imagined. Black holes became the ultimate proving grounds for general relativity, where every prediction could be tested against nature's most dramatic stage. One of the most striking confirmations came from the orbits of stars near the center of our own galaxy. Astronomers spent decades tracking the positions of these stars, capturing their motion year after year with exquisite precision. Instead of drifting in gentle orbits, several stars moved so rapidly and traced such tight curves that only a supermassive black hole could explain their behavior. The object they orbited, known as the central mass of the Milky Way, is millions of times heavier than Earth's lowercase sun, yet occupies a region smaller than the orbit of Mercury. These measurements provided some of the clearest evidence that black holes are not theoretical constructs. They are physical, gravitational engines shaping the dynamics of galaxies. Later, an even more remarkable discovery arrived. In 2019, the Event Horizon Telescope team released the first direct image of a black hole's shadow. By linking radio telescopes around Earth into a single global instrument, they captured a glowing ring of light surrounding a dark central region. This ring formed from the paths of photons skimming just above the event horizon before being flung outward toward Earth. The size and shape of the ring aligned almost perfectly with the predictions of general relativity. The dark center was not a surface. It was the shadow of the event horizon, a region of space-time from which no light could escape. The image confirmed that black holes behave exactly as predicted by Einstein's equations, not as exotic objects, but as geometric phenomena sculpted by curvature. The same principles that shape the horizons of black holes also govern the ripples they produce during mergers. When two black holes orbit one another, they gradually lose energy in the form of gravitational waves. These waves travel across the universe, stretching and compressing space-time as they pass. The detection of these waves in 2015 was a triumph, but the story did not end there. Each subsequent detection revealed new details about how black holes behave. The waveforms captured by detectors are not random vibrations. They are precise signatures. The rising tone of the inspiral, the sudden drop in amplitude at the moment of merger, and the fading ringdown as the final black hole settles into its most stable geometry match perfectly with Einstein's predictions. These waveforms allowed scientists to measure the masses and spins of the merging black holes, confirming that the final object always satisfies the rules of general relativity. No alternative theory could reproduce the precision of these signals. The waves also confirmed that black holes are not static. They vibrate, they ring, they behave like cosmic bells struck by their own mergers, and the frequencies of these vibrations correspond exactly to the curvature of space-time around them. black holes also offer a window into one of the greatest open questions in physics, the boundary between general relativity and quantum theory. At the event horizon, the classical picture of spacetime reaches its limits. Inside the horizon, where curvature grows without bound, Einstein's equations predict a singularity. This is a region where spacetime appears to collapse into infinite density and where the usual laws of physics cannot describe what happens. Scientists do not interpret this singularity as a literal place, but as a sign that general relativity is incomplete in extreme regimes. Quantum physics must modify this picture, but no theory has yet succeeded in providing a complete description. Black holes therefore stand not only as confirmations of what we know, but as markers of what we still have yet to understand. Yet even with these unanswered questions, the parts of black holes that can be observed behave with extraordinary consistency. Their influence on surrounding gas, their gravitational lensing signatures, their mergers, and their shadows all align with the predictions of curved spacetime. They are not anomalies. They are natural conclusions of Einstein's geometry, just as real as planets, stars, and galaxies. The universe contains objects where time slows, where spacetime wraps around itself, and where light is caught in perpetual loops. These places push physics to the edge, yet they remain firmly grounded in observation and evidence. As scientists continue to study black holes, they refine their understanding of how curvature shapes motion, how energy influences geometry, and how the universe behaves when pushed to its limits. Black holes are therefore more than mysterious cosmic traps. They are the clearest demonstration of the profound truth that emerged from general relativity. Gravity is not a pull. It is the shape of spacetime. And nowhere does that shape become more astonishing than at the edge of a black hole. Imagine, for a moment, that the universe is not a static stage, but a living structure, stretching and unfolding as time flows forward. Imagine that the galaxies scattered across the darkness are not fixed in place but drifting apart, carried by the expansion of spacetime itself. And imagine that this expansion was not discovered by watching galaxies move, but was first predicted by studying equations born from the curvature of spacetime. The idea seems almost unbelievable. Before telescopes revealed the truth, Einstein's theory already whispered that the universe could not remain still. Spacetime, curved and dynamic, demanded motion on the largest scales. That motion would eventually be seen in the shifting light of distant galaxies. But long before anyone measured it, the mathematics of general relativity had already traced its outline in the language of geometry. At the dawn of the 20th century, most scientists believed the universe was eternal and unchanging. Stars might flicker and planets might drift, but the cosmos as a whole was thought to remain fixed forever. Einstein himself initially shared this intuition and attempted to adjust his equations to preserve a static universe. Yet as mathematicians explored the consequences of general relativity, they discovered that a perfectly motionless cosmos could not exist. The equations required something more dynamic, something either expanding or contracting. A static universe would collapse under its own gravity or rip itself apart without a delicate balance. This revelation startled Einstein, who later called his attempt to force a static solution a mistake. The equations were speaking clearly. Spacetime wanted to move. While Einstein wrestled with this implication, a mathematician named Alexander Friedmann examined the field equations more boldly. He assumed a universe that was the same in all large-scale directions, and then allowed spacetime to evolve over time. To his surprise, the solutions revealed expanding and contracting universes, driven entirely by curvature and energy. These results were not speculative guesses. They emerged directly from the mathematics. If spacetime curves according to Einstein's rules, then the universe must evolve. It cannot remain fixed. Friedmann predicted cosmic expansion years before any telescope detected it. Around the same time, astronomers were refining their ability to measure the motion of distant galaxies. When they studied the light from these galaxies, they noticed something peculiar. The wavelengths were stretched, shifted toward the red end of the spectrum. This redshift meant the galaxies were moving away from Earth. Not just one or two galaxies, but most of them. The greater the distance, the greater the redshift. Edwin Hubble, who gathered these measurements with growing accuracy, recognized the pattern. The universe was expanding. Space itself was stretching, carrying galaxies with it. The observations aligned perfectly with Friedman's predictions and with the consequences of general relativity. The discovery changed everything. The universe, once assumed to be eternal and unchanging, was now understood to be dynamic, evolving, and shaped by the curvature of space-time. Expansion was not a motion of galaxies through empty space. It was the stretching of the underlying fabric. Every region of the cosmos participates in this flow, though the effect on small scales is too subtle to notice. Stars in a galaxy remain bound by gravity, and planets remain bound to their stars. But over billions of years, the large-scale structure of the cosmos expands in every direction. As scientists studied this expansion more deeply, they realized that the earliest light in the universe still carries the imprint of gravity. This faint glow, known as the cosmic microwave background, fills the sky in every direction. It is the cooled remnant of a much hotter early universe, stretched by billions of years of expansion. Embedded within it are tiny fluctuations, slight variations in temperature and density. These fluctuations reveal how gravity shaped the early universe, tugging matter into clusters that eventually grew into galaxies and stars. The cosmic microwave background is not just light. It is a fossil of space-time itself, preserving the geometric conditions of the universe when it was young. General relativity also explains why galaxies form in the structures they do. As matter gathered under gravity, space-time curved more strongly in some regions than others. These curved regions became wells where gas and dust collected, eventually igniting as stars. Over time, the curved structure of the universe grew more complex, forming galaxies, clusters, and vast filaments stretching across millions of light years. Each structure is a kind of cosmic fingerprint, shaped by the interplay of gravity and time. Yet the expansion of the universe holds one more mystery, one that even Einstein did not foresee. In the late 20th century, astronomers measuring distant supernovae discovered that the expansion of the universe is not slowing as expected, it is accelerating. The galaxies are moving apart faster and faster, as though something unseen is pushing space-time outward. Scientists named this unknown influence dark energy. It is a placeholder term, not a final explanation. We know the acceleration is real, supported by multiple independent observations. But the physical cause remains one of the deepest unsolved questions in modern cosmology. What matters for Einstein's theory is not the explanation, but the behavior. The equations of general relativity allow for such an acceleration. The expansion of space-time can speed up or slow down depending on the energy content of the universe. Friedman's solutions already contain these possibilities. Dark energy, whatever its nature, is simply the latest layer of mystery revealed by the curvature of space-time. The universe is not static. It is alive with motion. It expands, evolves, and bends according to the geometry that Einstein uncovered. Black holes shape the centers of galaxies. Time slows where gravity is strong. Light travels along curved paths. And on the grandest scales, space-time stretches, pulling galaxies apart as it goes. The expanding universe did more than overturn the old belief in a fixed cosmos. It revealed that space-time itself is an active participant in cosmic history, shaping and being shaped by the matter it contains. As scientists followed the implications of this discovery, they began to see that the large-scale structure of the universe behaves like a grand symphony conducted by the laws of general relativity. Every galaxy, every cluster, every filament of cosmic matter follows patterns whispered into existence by curvature. The idea that space stretches is not a poetic metaphor. It is a measurable, physical process that unfolds over billions of years, sculpting the shape of everything humans can observe. One of the clearest manifestations of this stretching appears in the light from distant galaxies. As space-time expands, the wavelengths of light traveling through it are stretched as well. What begins as visible light can arrive on Earth as infrared or microwave radiation, depending on how long it has traveled and how much the universe has expanded in the meantime. This stretching is not caused by motion through space, but by the expansion of space itself. Light becomes a kind of cosmic chronicle, its wavelength carrying the memory of the universe's growth. This phenomenon helps explain why we see the cosmic microwave background in its present form. In the first few 100,000 years after the beginning of cosmic expansion, the universe was hot, dense, and filled with light that scattered constantly from charged particles. As the universe expanded and cooled, this light finally began to travel freely. Over billions of years, space-time continued to stretch, lengthening the light into the microwave band, carrying with it delicate temperature variations. These tiny ripples, visible as faint patterns across the sky, reveal how matter and gravity interacted in the early universe. They show where density was slightly higher, where gravity began to pull matter together, and where the seeds of galaxies and clusters were planted. In this sense, the cosmic microwave background is a map of embryonic curvature, a snapshot of the universe when its structure was just beginning to form. The large-scale distribution of galaxies today reflects those ancient patterns. Cosmic surveys reveal that galaxies are not scattered randomly. They form enormous webs and filaments interconnected across hundreds of millions of light years. These structures trace the gravitational wells carved by fluctuations in the early universe. Matter flowed toward regions of stronger curvature, gathering into clusters and superclusters, while stretches of emptiness formed voids. The resulting pattern resembles a vast cosmic lattice shaped by gravity acting over billions of years. Without general relativity, the formation of such immense structures would be impossible to explain. Gravity's geometric influence not only draws matter together, but guides the path it takes as the universe expands. As astronomers studied the motion of galaxies within clusters, they encountered another mystery. The visible matter in these systems could not provide enough gravitational pull to hold them together. Something unseen had to be shaping the curvature more strongly than stars and gas could account for. This unseen contribution became known as dark matter. It does not emit light, does not reflect it, and does not interact with electromagnetic signals, yet its presence is undeniable. It influences the rotation of galaxies, the speed at which clusters move, and the lensing patterns that shape the paths of distant light. Dark matter is not speculation, it is an observational necessity. Although its physical nature is unknown, its effect on space-time curvature fits perfectly within Einstein's equations. The discovery of dark matter emphasized the flexibility of general relativity. The theory does not specify what matter must be made of. It simply states that whatever carries energy and mass will shape the geometry of space-time. Whether visible or invisible, ordinary or exotic, matter determines curvature. Dark matter therefore fits naturally into the framework, even if its microscopic identity remains a mystery. But the greatest surprise of all came when astronomers measured the brightness of distant supernovae. They expected the expansion of the universe to slow over time because gravity should pull everything inward. Instead, they found the opposite. The expansion was accelerating. Galaxies were moving apart faster than before. Something was counteracting gravity on the largest scales. General relativity allowed for such behavior, but the physical cause was unknown. Scientists introduced the term dark energy to describe whatever drives this acceleration. Like dark matter, dark energy is not a complete explanation. It is a placeholder that acknowledges a real, measured effect. The universe is speeding up, and the equations describing spacetime accommodate this acceleration, even if the underlying physics remains one of the deepest open questions in cosmology. While dark energy dominates the large-scale motion of the cosmos, gravity remains the sculptor of its structure. Over billions of years, matter collects under curvature, forming stars, galaxies, and clusters. These, in turn, influence the expansion through their gravity. The entire cosmos becomes a dialogue between matter and curvature, between the pull of gravity and the push of expansion, between the geometry Einstein uncovered and the unknown forces still waiting to be understood. This interplay shapes not only the distant universe, but the technology humans rely on every day. The expansion of spacetime itself does not affect small structures like solar systems or atoms, but the geometry described by Einstein permeates everything. Every cosmic observation, every satellite orbit, every gravitational wave detection depends on this curved, dynamic spacetime. The expanding universe is not an abstract backdrop. It is the stage, the actor, and the mechanism all at once. As the expanding universe revealed more of its structure, scientists began to understand that the growth of spacetime is not simply a backdrop to cosmic evolution. It is the engine driving the birth, motion, and destiny of galaxies. Every distant glow seen through a telescope carries within it the history of how space has stretched over billions of years. Every cluster of galaxies whispers the story of gravitational wells deepening and merging as matter gathers. Every faint ripple in the cosmic microwave background shows the earliest fingerprints of curvature, shaping what would become stars, planets, and observers capable of asking how it all began. This understanding brought forth a striking realization. The universe does not expand into anything. There is no outside region waiting to be filled. Instead, the distances within spacetime grow from within, like patterns unfolding on a living fabric. Galaxies move apart not because they are traveling through space, but because the space between them is increasing. Even though gravitational attraction binds galaxies together into clusters and binds stars into galaxies, the global expansion dominates at scales large enough. This duality between local curvature and cosmic stretch demonstrates the flexibility of general relativity. On small scales, gravity pulls matter inward. On the largest scales, the dynamics of spacetime govern the motion of everything. Einstein's equations also allow scientists to trace the universe backward in time. As the expansion is reversed in thought, galaxies draw closer together. The cosmic microwave background grows hotter, and matter becomes more compressed. Eventually, the extrapolation leads to a moment when the density of the universe becomes extremely high. This moment marks not a singular point in space, but a time when the universe was profoundly concentrated and hot. The early expansion from this state produced the matter and structure we see today. Although general relativity cannot describe the earliest fraction of a second when quantum effects dominate, it provides a clear picture of how the universe evolved from a hot, dense state into the vast cosmos observed now. The geometry of this evolution left signatures that scientists can measure directly. One such signature is the distribution of galaxies across large scales. The pattern of voids and filaments matching early universe predictions shows that gravity guided matter along the scaffolding etched into spacetime by tiny fluctuations. Another signature is the presence of light elements such as hydrogen, helium, and lithium in specific proportions. These proportions arise from nuclear reactions that occurred during the first few minutes of expansion, when the universe was still hot enough to fuse nuclei. The predictions match observations remarkably well, showing another link between cosmic evolution and the geometry governing it. The interplay between structure and expansion does not end with the early universe. As galaxies formed, their gravity slowed the local expansion in their neighborhoods. Clusters formed where matter pooled deeply enough to resist the global stretching of spacetime. Yet even these massive collections are carried along by the overall expansion, drifting apart from other clusters over billions of years. The universe becomes a mixture of local gravitational binding and large-scale stretching. with each scale following the rules set by Einstein's geometry. The discovery of acceleration added a layer of intrigue. Instead of slowing, the universe's expansion grows faster with time. Scientists measure this acceleration using not only supernovae, but also the distribution of galaxies, the distortions caused by gravitational lensing, and the patterns imprinted in the cosmic microwave background. The consistency of these methods leaves no doubt. The universe is accelerating. What remains unknown is the nature of the energy driving this acceleration. Dark energy fits the observations, but its physical identity is still hidden. Whether it is a property of space-time itself or a field permeating the cosmos remains one of the central unsolved questions in physics. Yet even this uncertainty highlights the strength of general relativity. The theory does not claim to explain what dark energy is. It simply provides a framework that describes how space-time evolves given the energy it contains. In this framework, the accelerating universe is not an anomaly, but a natural outcome of the equations. Dark energy, whatever it ultimately proves to be, acts as an ingredient in the geometry. The universe responds to it by stretching more quickly, reshaping the cosmic landscape on grand scales. As the expansion continues, distances between galaxies will grow so large that future observers billions of years from now might see fewer and fewer galaxies beyond their own. The cosmic web will remain, but the visible universe will appear to shrink as expansion carries distant structures beyond the reach of observable light. This outcome is not speculation. It follows from the measured acceleration and from the rules of curved spacetime. The universe is not drifting toward stillness. It is drifting toward a future shaped by the dominance of expansion. Through all of this, the central lesson remains clear. General relativity describes not only how matter moves through spacetime, but how spacetime itself evolves. The large-scale structure of the cosmos, the subtle glow of the cosmic microwave background, the drift of galaxies, and the acceleration of expansion all arise from the geometry Einstein uncovered. Gravity does not simply pull matter inward. It shapes how space-time stretches outward. The universe breathes through this geometry, expanding and evolving in a dance that has lasted billions of years and will continue far into the future. Imagine holding a device in your hand, a small piece of modern engineering that quietly listens to signals from satellites orbiting thousands of kilometers above Earth. It calculates your location with astonishing accuracy, guiding you through cities, across oceans, or along mountain trails. Yet hidden inside this simple act is a profound truth. The device works only because Einstein's ideas about time are correct. Without adjustments for the curvature of space-time and the effects of motion, the satellites that guide these signals would drift out of sync within hours, and the entire system would collapse into useless noise. The invisible geometry that shapes planets and stars also guides your daily steps. Relativity is not distant. It is woven into the rhythms of the modern world. The satellites used for positioning orbit Earth at high altitudes where the gravitational field is slightly weaker. Because of this, time flows more quickly for the satellite clocks than for identical clocks on Earth's surface. At the same time, the satellites move rapidly, and motion slows the flow of time according to special relativity. These two effects counter each other, yet they do not cancel. The gravitational time increase is larger than the slowing caused by motion. As a result, the satellite clocks tick faster than clocks on the ground. If this difference were ignored, even for a single day, the signals emitted by these satellites would drift so far that the system would miscalculate distances by many kilometers. Engineers must therefore correct for the geometry of space-time to ensure the satellites remain synchronized. Without general relativity, navigation systems would fail. This dependence on curved spacetime extends beyond navigation. Scientists have created atomic clocks so precise that they can detect differences in altitude as small as a few centimeters. If you lift one clock slightly above another, the higher one ticks faster because it sits in a region where gravity is weaker. This difference, although tiny, is entirely real. It reveals that time is not uniform across Earth's surface. The flow of time changes with height, just as Einstein predicted. These measurements are not exotic or hypothetical. They are performed in laboratories, using instruments so sensitive that even the gentle curvature of Earth's spacetime becomes measurable. Relativity also shapes the behavior of particles in accelerators. When particles approach the speed of light, their lifetimes stretch dramatically. Unstable particles that would decay in a fraction of a microsecond at rest can survive long enough to travel significant distances when moving at high speeds. This is not because the particles themselves change. It is because their motion slows the flow of time within their own frame. The extension of their lifetimes is a direct demonstration of time dilation, captured in experiments repeated countless times around the world. Particle accelerators, which probe the fundamental structure of matter, depend on the same principles that govern clocks in satellites. These technologies reveal a surprising unity between the small and the large. The same geometric rules that guide galaxies also guide the signals in your devices. The curvature of spacetime affects everything from the decay of particles to the functioning of modern communication networks. Satellites must account for gravitational time dilation. Accelerators must account for the slowing of time in fast-moving particles. Even Earth's rotation causes slight time differences between points on its surface due to their differing motions and gravitational environments. Engineers must consider these effects to achieve the precision modern systems demand. In this sense, relativity has become a tool rather than an abstract theory. It allows people to design instruments that rely on the precise flow of time. It allows scientists to measure gravitational differences in laboratories. It allows global networks to synchronize their operations. Without Einstein's insights, many modern technologies would fail or could never have been created in the first place. The geometry of spacetime is not merely a curiosity for astronomers. It is a foundation for practical engineering. What makes these applications so striking is that they confirm the geometric nature of gravity in everyday contexts. The bending of starlight and the merging of black holes are extraordinary events, but the shifting of time in a handheld device is just as real. Each reveals that gravity is not a force acting across space, but the expression of spacetime's curvature. Every technological system that relies on precise timing becomes a testament to this truth. The clocks in satellites run at different rates, not because of mechanical differences, but because time itself flows differently in different places. Einstein's theory therefore becomes a bridge between cosmic phenomena and human experience. It transforms time from a silent background into an active participant in technology. It shows that the same equations governing the vastness of the cosmos govern the accuracy of signals exchanged between devices on Earth. The map guiding you through a city is connected, in the deepest sense, to the curvature that shapes the motion of planets and the behavior of stars. The more scientists and engineers relied on relativity, the more they discovered that even the smallest differences in gravitational potential can influence the flow of time in measurable ways. What once seemed like an abstract prediction now reveals itself in laboratory experiments, technological networks, and even everyday environments. Time is not a universal rhythm. It is a local property shaped by Earth's curvature, by altitude, by speed, and by the geometry Einstein uncovered. Each modern measurement confirms that the universe is far stranger and more intricate than the classical picture once suggested. One of the most delicate demonstrations of this truth came from experiments using optical lattice clocks, instruments so precise that they lose less than a second over billions of years. When scientists place two of these clocks just a short distance apart, with one slightly higher than the other, they tick at different rates. The effect is tiny, yet the clocks record it flawlessly. A shift of only a few centimeters changes the gravitational environment enough to alter the flow of time. Such experiments show that time is not simply measured, it is sculpted by gravity. The gentle curvature around Earth is enough to create distinct temporal rhythms at different heights. These measurements confirm that gravity acts not through a pull, but through the geometry of spacetime, resetting the pace of time itself. This sensitivity to altitude has profound implications. Scientists can use clocks to map Earth's gravitational variations, creating a kind of gravitational topography. Valleys and mountains influence the flow of time slightly differently, and these differences can be detected with modern instruments. Time becomes a measuring tool, capable of revealing the shape of Earth's gravitational field. This capability helps geologists study changes in underground water, assists engineers in refining global navigation networks, and opens new windows into Earth science. All of it is made possible because general relativity describes how time responds to curvature. Relativity also plays a role in communication networks. Systems that require precise synchronization, such as financial exchanges, scientific observatories, and global data networks, depend on accurate timing signals. If clocks drift due to gravitational or motion-based differences, entire networks can fall out of alignment. Engineers correct for these differences continuously, ensuring that timing signals remain coherent. This invisible layer of relativity allows global systems to function smoothly. Without these corrections, messages would arrive out of order, data would misalign, and technological systems that seem stable would begin to fail. Every synchronized signal is a quiet acknowledgement that time does not flow uniformly. Even within transportation systems, relativity leaves a signature. High-speed aircraft, like satellites, experience time differently from stationary objects on Earth. Pilots traveling long distances at high speeds experience slightly less elapsed time than observers who remain on the ground. The difference is extraordinarily small but real. Over long periods, such deviations accumulate, and precision instruments must account for them. In this way, human motion interacts directly with the geometry of spacetime, altering the passage of time even during ordinary travel. One of the most dramatic demonstrations of relativity in action occurs in particle accelerators. By accelerating particles to speeds close to the speed of light, scientists watch their lifetimes stretch in ways impossible to explain without time dilation. When unstable particles decay, they do so according to the flow of time they experience. If time slows down for them due to their motion, their decay takes longer from the perspective of outside observers. These extended lifetimes confirm that time itself adjusts to motion, just as Einstein predicted. Particle accelerators therefore do more than reveal the building blocks of matter. They reveal the behavior of spacetime. Relativity also influences astronomy. When telescopes observe signals from distant pulsars or neutron stars, they must account for the gravitational environment through which the signals travel. Curved spacetime affects the timing of these signals, stretching or compressing them depending on the gravitational fields encountered. Without correcting for relativity, astronomers would misinterpret the data. Instead, they use relativity as a foundation, allowing them to decode the timing of pulsars, the orbits of distant systems, and the gravitational dance of binary stars. Even the synchronization of telescopes across Earth requires relativistic corrections. When observatories link their instruments to form a single virtual telescope, the signals they gather must be combined with extreme precision. The timing differences caused by Earth's rotation, its gravitational field, and its motion through space all shape the data. Only by treating time as a curved dynamic quantity can these signals be brought into perfect alignment. This method was essential for producing the first image of a black hole, where telescopes across the globe captured light from the edge of an event horizon. In all these cases, relativity does not appear as a distant cosmic law, but as a practical necessity. It permeates the modern world. It ensures the accuracy of navigation, communication, scientific measurement, and even the basic functioning of global technology. Time dilation, gravitational redshift, frame dragging, and the curvature of spacetime are woven into systems that millions of people rely on every day. Einstein's insight that gravity is geometry does more than explain the motion of stars. It links the cosmos to daily experience. It transforms time into a measurable, flexible dimension that responds to altitude, speed, and mass. Every modern device that coordinates time participates in this geometric dance. Every satellite orbiting Earth experiences a different flow of time, and every correction applied to keep the system aligned stands as a demonstration that relativity governs the world at every scale. As the role of relativity in technology deepened, scientists began discovering that the same geometric principles that shape the cosmos can be harnessed to probe Earth itself with extraordinary sensitivity. Time, once thought to be a uniform backdrop, became a tool for measurement. Gravity, once thought to be a force, became a map of curvature that engineers could navigate. The closer humans looked, the more they found that even the smallest details of modern life depend on the precision that general relativity demands. One of the most striking examples of this involves networks of satellites working together to maintain global communication and navigation. Each satellite orbits Earth at a slightly different speed and altitude, which means each satellite experiences a different gravitational environment and a different flow of time. Engineers must constantly adjust these clocks, ensuring that every satellite's rhythm aligns with the geometric predictions of general relativity. Even a tiny error would cause signals to drift, creating large positional inaccuracies. The fact that navigation systems function reliably proves that Einstein's description of time curvature is not a philosophical idea. It is a practical reality built into the hardware orbiting above the planet. Another remarkable application arises in the study of Earth's interior. Scientists use time-sensitive measurements from satellites and ground-based clocks to detect tiny variations in Earth's gravitational pull. When underground water levels change, when ice melts or accumulates, or when tectonic plates shift, the curvature of space-time around Earth changes slightly. Sensitive clocks can detect these changes. This technique, known as a relativistic geodesy, allows researchers to study Earth's structure and motion without drilling or direct sampling. Time becomes a probe, revealing the invisible movements of mass beneath the surface. Relativity even influences the paths spacecraft take as they travel through the solar system. Navigators must account for the curvature of space-time around planets, moons, and the lowercase sun to plot accurate trajectories. Signals sent to and from spacecraft travel through a curved space-time, causing delays that must be calculated precisely. Without these corrections, spacecraft would miss their targets or drift off course across millions of kilometers. When missions land on distant worlds or perform flybys within narrow margin windows, they do so by following paths shaped by Einstein's geometry. The same principle applies when astronomers measure the positions of stars. Earth's orbit carries it through regions of space-time with slightly different gravitational potentials, and these variations influence the timing of signals received from distant stars. High-precision astronomical surveys must correct for relativity to ensure that the positions and motions they catalogue are accurate. Even the simple act of measuring a star's light becomes a dialogue with the curvature of the universe. In atomic physics, the curvature of space-time influences the calibration of fundamental constants. When scientists compare clocks located in different laboratories around the world, they must correct for Earth's gravitational field and for the rotation of the planet. Without such corrections, measurements of fundamental constants, such as the frequency of specific atomic transitions, would differ from one laboratory to another. Relativity ensures consistency. It unifies the flow of time across the planet by providing the rules that account for gravity's influence. These applications demonstrate a profound unity between the nature of the universe and the structure of human technology. The same geometry that shapes the orbits of stars also shapes the circuits and signals that guide modern life. Every experiment, every measurement, every technological system built on precise timing reflects the same principle. Gravity is geometry, and time is part of that geometry. The devices humans build must operate within that framework. What makes this even more extraordinary is that all these effects are small compared to the dramatic curvature near black holes or neutron stars. Earth's gravitational field is gentle, yet its curvature still influences time, motion, and light with measurable consequences. If Earth's gravity creates such subtle shifts, then the universe must be filled with far greater variations in the flow of time. Each star, each galaxy, each cluster shapes the geometry differently, creating a vast landscape of temporal differences across the cosmos. General relativity therefore becomes more than a scientific theory. It becomes a kind of cartography, a map that describes how time and space flow around every form of matter and energy. Technology is simply humanity's method of navigating that map. When satellites synchronize their clocks, when telescopes adjust their signals, when accelerators track the decays of particles, they are all responding to the same deep structure. In this way, the universe becomes both the teacher and the environment. It teaches through the precise behavior of clocks and particles, showing that time bends under gravity. It provides a setting where satellites must obey the rules of curved spacetime. And it reveals, through the successful operation of these systems, that Einstein's insight was not merely theoretical. It was a description of the real physical world. From the moment Einstein revealed that gravity is not a force, but the curvature of spacetime, scientists faced a daunting question. How could something so intangible be measured? How could human beings trace a bend in time itself or detect the stretching of space as it flows across the cosmos? The challenge seemed almost beyond imagination. Yet step by step, experiment by experiment, the invisible structure of spacetime has been made visible. Not by direct touch, but by listening to the universe through light, time, and motion. Each instrument built to study gravity has become a kind of compass for navigating the geometry that shapes everything we see. The first great breakthrough came from observing how light bends when it passes near massive objects. This bending is not caused by a force pulling on the light. Instead, the path of the light follows the geometry carved by mass. When distant galaxies shine through clusters of matter, their light stretches into arcs, rings, and distorted shapes. These patterns, known as gravitational lensing, act like fingerprints of space-time curvature. By studying these arcs, scientists can map the distribution of matter, both visible and invisible. Dark matter, which does not emit light, reveals itself through lensing, forming vast filaments across the cosmos. This lensing is not theory, it is observation. It is the geometry of the universe traced through the pathways of ancient starlight. As instruments advanced, a new tool emerged: pulsars. These rapidly spinning neutron stars emit beams of radiation with astonishing regularity. Each pulse arrives like the heartbeat of a distant clock. If spacetime shifts even slightly, the arrival times change. By studying a network of these pulsars scattered across the sky, scientists created a galaxy-scale detector. Subtle timing variations reveal passing gravitational waves from distant supermassive black holes spiraling toward collision. These waves ripple across thousands of light years and stretch spacetime in ways impossible to detect by any other means. Pulsar timing arrays therefore become a way to listen to the deep architecture of the galaxy. Closer to Earth, atomic clocks offer another form of mapping. These clocks tick with such precision that lifting one by a few centimeters causes it to run measurably faster due to weaker gravity at higher altitude. Time itself becomes a tool for measurement. By comparing clocks at different locations, scientists can build detailed maps of Earth's gravitational potential. Variations caused by underground water, shifting rock layers, or melting ice become visible through the flow of time. Earth's own curvature of spacetime reveals its secrets through the ticks of these extraordinary clocks. Another method arises from the study of binary neutron stars. When two neutron stars orbit one another, their immense mass curves spacetime so strongly that their orbit decays as they emit gravitational waves. By measuring the changes in their pulse timing, scientists can calculate exactly how much energy they lose and how the curvature evolves. These systems become laboratories for studying strong gravity, confirming Einstein's predictions in extreme environments far from Earth. On even larger scales, the cosmic microwave background holds the oldest map of spacetime. This faint radiation, bathing the sky from every direction, contains tiny variations in temperature that reflect the curvature of the early universe. These patterns reveal how matter clumped under gravity, how space-time expanded, and how the cosmic web formed. By studying them, scientists determine whether the universe is flat, curved, or open on the grandest scales. The result is clear. Space-time is nearly flat overall, shaped by the balance of matter, radiation, and dark energy. Gravitational wave detectors add a final layer of insight. These instruments, stretching across kilometers, measure tiny changes in length as passing waves ripple through Earth. They detect black hole mergers, neutron star collisions, and cosmic tremors billions of years old. Each detection adds a point on the grand map of space-time. These waves are not metaphors. They are vibrations in geometry itself, measured directly by human technology. Together, these tools form a single tapestry. Lensing traces curvature across galaxies. Pulsars trace it across the Milky Way. Atomic clocks trace it across Earth. Gravitational waves reveal its dynamic motion. The cosmic microwave background reveals its ancient shape. Piece by piece, the invisible has become visible. Space-time is no longer an idea. It is a mapped, measured structure, shaping the universe and evolving with it. Even with every triumph, every measurement, and every confirmation of Einstein's vision, the universe remains filled with unanswered questions. General relativity has mapped the geometry of space-time with breathtaking accuracy, yet it leaves the deepest mysteries untouched. It tells us how gravity works, but not why space-time has the form it does. It shows how curvature shapes motion, but not what space-time is made of. As powerful as the theory is, it stands like a magnificent bridge ending at the edge of a cliff, pointing toward a landscape not yet explored. One of the greatest unanswered questions lies at the intersection of relativity and quantum physics. The two frameworks describe different aspects of nature with extraordinary precision, yet they refuse to merge. General relativity treats space-time as smooth and continuous. Quantum physics treats energy and fields as discrete and probabilistic. When these ideas collide in places like the centers of black holes or the earliest moments of the universe, the mathematics breaks down. Singularities appear, signaling that our theories are incomplete. Something deeper must exist, something that explains how space-time behaves at the tiniest scales, but no experiment has yet revealed its structure. Another profound mystery is dark matter. Observations show that galaxies rotate too quickly for their visible matter alone to hold them together. Gravitational lensing reveals vast structures of invisible mass. The cosmic web itself depends on matter we cannot see. This unseen mass shapes most of the curvature in the universe, yet we do not know what it is. It does not emit light. It does not interact strongly with known forces. It reveals itself only through gravity. Whether it is a new type of particle, a hidden field, or something stranger remains unknown. Even more enigmatic is dark energy. The expansion of the universe is accelerating. This is not speculation. It is measured through supernovae, galaxy clustering, and the cosmic microwave background. Something in the fabric of space-time is causing large-scale repulsion, stretching the universe faster over time. We do not know what drives this acceleration. It may be a property of space-time itself or a field filling the cosmos. It may reflect a deeper layer of geometry waiting to be uncovered. Dark energy is not a small puzzle. It dominates the energy content of the universe. There are more mysteries still. What happens to information inside black holes? Does it vanish, remain encoded in the horizon, or escape in some subtle way? Does space-time emerge from quantum entanglement, hinting at deeper structure behind the geometry we observe? Why does gravity seem so weak compared to other forces? What sets the shape of the universe? These questions do not undermine relativity. They reveal its limits, just as Newton's laws remain true within their domain, even though relativity extends beyond them. The universe also challenges us with the question of time, itself. Why does time have a direction? Does the flow of time arise from entropy, from geometry, or from some deeper principle? General relativity describes how time bends and slows, but not why time exists as a dimension at all. The answers to these questions may lie in physics not yet discovered. Despite these mysteries, one truth remains unshaken. Einstein's insight changed our understanding of the universe forever. He revealed that gravity is not a pull, but the shape of space-time. He showed that time slows near massive bodies, that light follows curved paths, and that the universe expands. Every experiment has reinforced this geometric view of reality. Even the mysteries point back to it. The story does not end with what we know. It continues with what we do not. The universe invites exploration. It invites deeper theories and sharper instruments. It opens paths that Einstein could not follow, but that future generations will. Gravity arises from space-time. Space-time includes time, and time remains the silent architect shaping the universe. Einstein did not merely describe gravity. He revealed that time itself shapes the cosmos.